Good morning, everyone. We now continue with integration. We were dealing with powers of sine and cos. Now let's deal with powers of tan and cot. Okay, so what we're going to be dealing with right up to the power 3. So let's start with the basic integral of tan. So we got the integral, so let's make this k tan bx. So when you integrate tan, you will find the straight on the formula sheet. It's a standard integral. So when you integrate tan, remember k and b are constants. So k and b are constants. So this applies basically only if k is a number and b is a number too. Okay, so when you integrate tan, you're going to get basically k ln absolute value of sec bx all divided by b plus c. That is a standard integral for tan. But if you're wondering how did we get the integral of tan, let me just show it to you quickly. So how did they get that formula ln of sec? So if we go back to our N4 work, remember that when you have the integral of f prime x all over f of x, well, actually it's N5 stuff. So this is the division type. You remember when the numerator is an exact derivative of the denominator. So if I ask you to integrate tan, now let's assume that you forgot or you could not find that on the formula sheets. Right. So how do we get ln of sec? So we know that tan can be written as sine x over cos x. Right, so tan is sine over cos. So now this satisfies the condition f prime x over f of x. So if you look here now, let me just redo this. I got sine x, cos x. Now let's compare. My f of x here is cos. F prime x is almost the derivative of cos. So what is the exact derivative of cos? The exact derivative of cos is going to be minus sine. But we know originally there was a positive there. Can you see that? So by inspection, all I do is multiply by -1. So a negative times a negative will give me a positive. So therefore, if I got k f prime x over f of x, then the answer is always k ln absolute value of the denominator plus c. So now this satisfies the condition. Can you see that? I got my f prime x, which is minus sine x, f of x, which is cos, my constant in front, -1. So therefore, this is equal to -1 ln of the denominator, which is cos, plus c. Right. Now you might be wondering, that does not look like cos, that is sec. So with just a little bit of simplification here, we will get to that. So now I got minus ln of cos, so that's going to be ln cos x from my exponent, not exponent laws, from my log laws. If you have a number in front, you can bring that number up and make it a power. So remember, if I have something like log of 4, this is the same as log of 2 squared, which is the same as 2 log 2. So I can take 2 to the top, just like here, and I can bring it down. That is your log law. So what I'm going to do here is I'll take this to the top, and it becomes a -1. Can you see that? So now we got ln cos to the power -1 exponent law. X to the power -1 is the same as 1 over x. So this is going to be 1 over cos. Cos to the power -1 is 1 over cos. So now, from your trigonometry, your identities, 1 over cos is sec. So that is how we get the formula ln of sec. Okay. Now, you do not have to go and derive it this way. But it's just for your understanding. You're wondering now, obviously, where did ln come from? You know, where does ln come from? Only when you have the division type, when your numerator is an exact derivative of the denominator, that's the only time you take ln of the denominator. Right, so this is straight on your formula sheet, so that is 10. Now, let's take an example. If I ask you to integrate 2 times the integral of tan 3 over 2x, you don't have to go and do it that way. All you do is straight follow what's on the formula sheets. So here I'm integrating, that's my 2, tan of 3 over 2x. So my b here is 3 over 2, k is 2. So I'll integrate it, that's going to be 2 ln absolute value of sec 3 over 2x. So I got it sec of bx all divided by 3 over 2 plus c. And you're done. That's a standard integral for 10. Now remember, I'm dividing by 3 over 2, which is the same as multiplying by 2 over 3. So therefore, I get 4 over 3 ln sec 3 of absolute value 3 over 2x plus c. We're done. Right, so this is nothing new. We got it straight. We were dealing with the integral of 10 in N4 also. Now, let's take 10 squared. Right, so now 10 squared. Now, what did you differentiate that will give you 10 squared? There's no standard derivative that will result in 10 squared. Okay, we know that when you differentiate 10, you get sec squared. But there's nothing that gives you 10 squared directly. You check. You know your table of derivatives. So, what we need to do is rewrite this in a different form. So what can we do? We got 10 squared, so we're going to use our square identity here. Right, so now you don't have to worry. When it came to sine and cos, there were 2 different formulas that we were using. We were using our double angle formula and we were using our square identity. That all depends on your exponents. But here, it's only square identity. So the square identities are given to you on the formula sheet, but it's best to know it. So we know that 1 plus tan squared bx is equal to, from your square identities, sec squared. So I know that 1 plus tan squared is equal to sec squared. So if I make tan squared the subject of the formula, tan squared will equal to sec squared minus 1. Okay, so now I can go and replace tan squared. So that's going to be k there, which represents a number. Remember, this k represents a number here. So we got the integral of, and then I'm replacing tan squared with sec squared minus 1. Now, why do we change it to sec squared? Because sec squared, we know, what do you differentiate that results in sec squared? It's going to be 10. Okay, so basically when you integrate sec squared, you will not find this directly under integration on the formula sheets. But you need to remember, what did you differentiate that resulted in sec squared? And that will be 10. So don't forget, that's tan of bx all divided by b. Here we're integrating minus 1 with respect to x. That's minus x plus c, and you're done. Right, so it's just a standard square identity here. Whenever you see tan squared, replace it with sec squared minus 1 first, and then integrate. So here's another example here. Here's an example of this formula. So I've got tan squared x over 3. All I will do is change it. Tan squared can be written as sec squared 1 over 3x minus 1. Remember, x over 3 is the same as 1 over 3x. Now, I got my sec squared, so I know when I integrate sec squared, it will be tan 1 over 3x, all divided by 1 over 3. Integrate minus 1, that will be minus x plus c, and we're done. Be careful, you also got the 4 here, but you do not have to multiply it inside, you can leave it there. Remember, you got a fraction here. This is 1 divided by 1 over 3, which is just 3 over 1 times tan of 1 over 3x minus x plus c. If you want to remove the brackets, you can, but it's unnecessary. Remember, if you differentiate tan, what is the derivative of tan? The derivative of tan 1 over 3x is going to be sec squared 1 over 3x times 1 over 3. How do you check your solution? Use differentiation. So let's do this here. So remember that if y is equal to k tan f of x, this is our table of derivatives, then the derivative of tan f of x is going to be sec squared f of x times the derivative of f of x, which is f prime x. So here, if I want to differentiate 3 tan 1 over 3x, so if I have 3 tan 1 over 3x, which is my k tan f of x, then you differentiate this. The derivative of 3 tan 1 over 3x will be 3 times sec squared 1 over 3x times, so where am I at the moment? I'm k. I'm at here k sec squared f of x times f prime x. You should be checking, practicing your differentiation every time. So that's 3 sec squared 1 over 3x times the derivative of 1 over 3x, which is 1 over 3. So what happens here? 3 times 1 over 3. That will cancel, so I've got the sec squared 1 over 3x. So let's check this. What did we have here? There's a check, you can see that. Sec squared of 1 over 3x. I'm just checking the sec squared, showing you your differentiation. Alright, so that is tan and tan squared. Simple. Tan is given to you straight on the formula sheet. Tan squared, use your square identity. Now, let's deal with tan to the power 3. So I got k there, tan to the power 3 of bx. So we got this odd power. What do you think we're going to do to the odd power? We got an odd number. So what we're going to do is we're going to split the odd power. Just like how we split it sine to the power 3 and cos to the power 3, we split up tan to the power 3. So if I'm splitting this up, this is going to be tan to the power 1 times tan squared. So now I split my odd power. What do you think I'm going to do next? I got tan squared. I'm going to use my square identity here. So this is equal to k the integral of tan bx, change your, or rewrite tan squared as sec squared of bx minus 1. Now, what do we do from here? Right, there's two ways to deal with this from here now, okay? So one way would be to remove the brackets. That's the way I'm going to deal with first, because now we're going to deal with this as two separate problems here, because there are two terms. Let me remove the brackets completely, just like how we did with when I first showed you sine to the power 3. So what am I going to do now? I'm going to multiply k tan bx times term 1 and then k tan bx times term 2. So now I got my k, the integral of tan bx times sec squared bx dx. So that's my term 1. And then k tan bx times negative 1, which is going to be minus k integral of tan bx dx. Okay, now what do you notice? These two terms, they are completely different in terms of how we're going to integrate them. The second one, k tan bx, well, that's straightforward here. There's it here. We know the solution for this here. Can you see that? So that is not a problem. The problem is term 1. Okay, so term 1, what do you recognize about term 1? You check it, what do you recognize? There's a tan. Look at it. There's a tan multiplied by the exact derivative of tan, which is sec squared. That means it deals with exact derivative, the multiplication type. Right, so that's the first type we've been dealing with. So let's deal with that multiplication type now. So when I talk about multiplication type, I mean when you have k, the integral of f of x to the power n multiplied by f prime x dx, and this formula has a condition: your power must not be negative 1. Okay, so here, in a situation like this is going to equal to k f of x to the power n plus 1 over n plus 1 plus c. This is by inspection, and you know we can also do this by u substitution. Okay, so by inspection, let me just do inspection on the top here. Here I will do u substitution. Okay, you can do the u substitution. What will you let u equal to in a case like this here? You let u equal to 10. You always let u equal to f, not f prime, not the exact derivative. Because the whole idea is for sec squared to cancel there. I can do this by inspection. So by inspection, if I have the integral of, I got tan bx there. There's my tan bx, there's my k here. So multiplied by sec squared bx dx. So what's missing in order for it to be a 100% exact derivative here? What is the derivative of tan bx? The derivative of tan bx is sec squared bx times the derivative of bx. So what's missing here? B. So if I write down b there, I divide by b there. You clear with that? Because b over b will be 1. So now what's happening here? It satisfies the condition k f of x to the power n. So here is your coefficient. So this can be written as k over b, which is your constant. And then I got f of x there, which is tan bx. And then the formula is n plus 1 over n plus 1. So the power here originally was 1. So 1 plus 1 is 2 over 2. And then obviously plus c. So this is by inspection. Okay, doing it in one step. So this will equal to k over 2b times tan squared bx plus c. Right, so that is by inspection. But now most people have a problem with doing inspection. The problem is when it comes to cancelling your fractions here. So the safer way to do it is your u substitution. You cannot go wrong with u substitution. Okay, as long as you know what to let u equal to. So in this case, what will I let u equal to? Obviously, always let u equal to f of x. So I'm going to say let u equal to tan bx. Then you're going to find du over dx. What is the derivative of tan bx? We just did it there. The derivative of tan bx is going to be sec squared bx times the derivative of bx, which is b. Now I will make dx the subject of the formula. So therefore, dx is going to equal to du divided by b sec squared dx. Right, so I decided to use substitution. I showed you inspection there. Right, this is the u substitution technique. Applying, when I say let u equal to tan bx, it only applies to this term 1. It does not apply here. This is a completely different problem. So here, let's go back up. We substitute, so that's my k, the integral of tan bx. But now, tan bx is no more tan bx. It's replaced with the letter u. So that's going to be u times sec squared bx. So that's going to be sec squared bx times dx. And your dx is, there's your dx here. You can see your dx. Your dx is du divided by b sec squared bx. So that's going to be du divided by b sec squared bx. So clearly you can see sec squared and sec squared will cancel. So you end up with k on the top, b in the bottom, just u to the power 1 du. Now I can integrate with respect to u. So this will be k over b, and u to the power 1 plus 1 will be 2 over 2. All we have to do is substitute back. So this is going to be k over 2b. And what was u? My u, there's my u here. U was tan. So that is tan bx. So that is just term 1. So term 1 involved exact derivatives. So you can see you must know your derivatives. If you don't know the derivatives, there's no way you can make it in N5. Because you can see we're doing integration, but 70% of the knowledge required involves differentiation. Even 90% of the problem, I would say, involves differentiation. Right, so don't forget term 2. We did not integrate term 2. So term 2 was the integral of tan bx, and this is a standard integral, number 1, which you will find on the formula sheet. Integrate tan, so that's going to be ln absolute value of sec bx all divided by b plus c, and you're done. So let me just copy it down here. So that's minus k over b ln sec bx plus c. So that is the first technique dealing with tan to the power 3. So you can copy this down. We're going to redo this now. I'm going to redo this example now without removing the brackets. Right, so let's deal with method number 2. Let's see what is the difference. Okay. So the first two steps will be the same. You have an odd power, split the odd power. So that's going to be 10 to the power 1 times 10 squared. So we split the odd power. Then we have 10 squared. We use our square identity. That's going to be k 10 bx. And then 10 squared, we know from our square identities, remember that 1 plus 10 squared of bx is equal to sec squared. So that's our square identity. We are rewriting 10 squared. So we go 10 squared is equal to sec squared minus 1. So all I'm going to do is replace this with sec squared minus 1. Now, what happens if, or what will happen if you let u equal to sec bx? Right, because you're noticing now there's a power here, and you might notice that it's a little bit similar to the previous examples when we were dealing with cos to the power 3. When we came to a step like this, we used our u substitution. So, now the derivative of sec is definitely not 10. The derivative of sec is sec times 10. So it's not 100% exact derivative where we can, in fact, it's not even a derivative. It's not something where we can just do it by inspection. So let's see what happens. But let u equal to sec bx. Okay. So then the exact derivative of sec. So what is the derivative of sec? The derivative of sec of bx will be sec bx times tan bx times the derivative of bx, which is b. Right. So now I can make dx the subject of the formula. So dx is going to equal to du all divided by b sec bx tan bx, which is actually du divided by b. Now, what did we let sec bx equal to? We let it equal to u. We have sec bx here again. Can you see that? So I can replace it with u. So I got my u there, and then I have tan bx. Now let's substitute and see what happens. So here I got my k times, remember k is a number, I got my tan bx there. Now remember that sec is u. So this is not sec, this is sec raised to the power 2. So therefore this will be u squared. You're clear with that? Now dx, there's my dx here. Dx is divided by du. So dx is equal to du divided by b u tan bx. So that's going to be du divided by b times u times tan bx. What do you notice now? Tan bx and tan bx cancel. So now let's write down what remains. Our constants, well, we got this number here, which is b. It's actually 1 over b. Multiply it by whatever you have in front. So that's k on the top divided by b in the bottom. We can see that tan and tan cancel there. So the derivative there cancelled. What remains now? What remains in the numerator is these two terms, u squared minus 1. But that's not the only thing that remains. What else remains here? U in the denominator. So there's my u in the denominator. And now we are integrating with respect to u. So we can simplify this further now. Right, if we go back to our N4 type problems where you're just given x squared minus x all divided by x, simplify and integrate. So it's just that we're going to do it with respect to u. So that's going to be k over b. Simplifying this, I'm going to separate them into two fractions. Why? Because there are two terms in the numerator. So that's going to be u squared over u minus 1 over u. So now, we use our exponent laws. When we are dividing and the bases are the same, write down your base once, subtract 2 minus 1, you just get 1 there. So u squared over u is just u. 1 over u is 1 over u. You do not take u to the top. Okay, you know that. Do not take u to the top because you'll have a negative 1. Right, and you know the rule is you cannot have negative 1 as an exponent because minus 1 plus 1 will give you 0 and 0 in the denominator there. So we integrate with respect to u. So that will be 1 plus 1, which is 2 over 2. Integrate 1 over u. This is your division exact derivative, the one that we just did now. So that's going to be minus ln u plus c. And you're done. Don't forget to substitute back for u. Don't forget to substitute back. What was u? U was sec of bx. Alright, so this was option number 2, method number 2. It's up to you, whichever one you want to use. But this is correct. If we have to go and use our square identity, sec squared is equal to 1 plus tan squared, we can change this to, let's look at the other solution there we had. Final answer was, okay, we got the minus ln sec. So if I multiply k over b times minus ln sec is minus k over b ln sec, you can see there's it here. This matches with this one. Only here you got sec squared and the other solution had tan squared. So if you want to rewrite this, just to show you that it's equal. You might have an extra constant, but you know the constant doesn't matter. You always put down plus c there. Right, so that was 10 to the power 3. Let's take an example. You can try and work this one out now. It's up to you, whichever method you want to use. Right, so due to time constraint, we're going to deal with this quickly. So we have an odd power. So that's going to be, split it up, so that will be tan 3 over 4x times tan squared 3 over 4x. Split the odd power. It's just a method, very simple to deal with. So tan squared, we use our square identity. Tan squared can be written as sec squared 3 over 4x minus 1. Now from here you have two options. One is let u equal to sec, the other one is remove the brackets. I'm going to go with option number 1 now because I want to get to the solution fast because of time. Right, so now I'm going to remove these brackets. It's going to be 1 over 2 tan 3 over 4x times sec squared 3 over 4x dx. Don't forget your integral and dx. We are separating this completely into two different problems. So it's half tan times term 1 and then half tan times term 2. So that's going to be minus 1 over 2, the integral of tan 3 over 4x dx. I remove those brackets. Can you all see that? Now I'm going to use the method of inspection. It works when you are in a hurry. Okay, like now. So now I got my 1 over 2, the integral of tan 3 over 4x, then I got my sec squared 3 over 4x, and I'm checking for the exact derivative there. So the exact derivative of tan 3 over 4x is going to be sec squared 3 over 4x multiplied by 3 over 4. That's the only thing that's missing. So if I put 3 over 4, I need to cancel 3 over 4 because there was no 3 over 4. And the only way to cancel it is to multiply by 4 over 3. Because 4 and 4 cancel, 3 and 3 cancel. So now I can go straight to my solution. That's going to be, okay, 4 times 1, which is 4, divide there. So that's going to be 2 over 3. You can simplify that. The main thing is you got f of x, which is tan 3 over 4x, all raised to the power 2 over 2. That is method number 1. Here, straightforward, you know this is a standard integral. So when you integrate tan, it's going to be ln absolute value of sec 3 over 4x, all divided by 3 over 4 plus c. And you're done. You can see, once you know inspection, everything becomes simple. Right, so now that's going to be 1 over 3 tan 3 over 4x all squared. Here, I got 1 over 2. I'll multiply by 4 over 3. So that's going to be 2 over 3 there. Ln sec 3 over 4x plus c. Okay, so what happened here? That was minus 1 over 2 multiplied by 4 over 3. That's what happened there. Fraction divided by fraction. 4 divided by 2 is 2. And I got my 2 over 3. So that was method number 1. Inspection, it works fast. You can see that.